Right. So we're now talking about section 3.1, norm spaces and Banach spaces. And we had a little introduction to this last time. We looked at the 4 norm space axioms. I'd also mentioned semi-norms, which have the same connection with norms as pseudometrics have to metrics. And we're going to be talking about real norm spaces or complex norm spaces in this module. Obviously, norms connect to metric spaces. That is, every norm gives you a metric. Of course, there are plenty of metric spaces where the metric doesn't come from a norm. And if you want something that's very different from a norm space, then you could use the discrete metric. And that's very, very different from any kind of metric you would get from a norm. So then we looked at norms on R to the n and on real continuous functions on the unit interval with some norms sub p, meaning different things for the two spaces, but same notation and the same sort of connection between them. And so we defined those, and what do we have? Yes, so on R to the n, if p is less than infinity, 1 less or equal to p less than infinity, then you use the sum of the p powers of the modulus, and then take the p root, whereas for the uniform norm, or the sup norm rather, you just take the max of the coordinates, which is the same as the supremum of the coordinates, the modulus, that is, of the coordinates. You can show as an exercise that if you let p tend to infinity, the p norms do tend to the right thing. And the same goes for continuous real-valued functions on the unit interval. Integrals correspond to sums. So where we had a sum before, we now integrate the p power of the modulus of the function, and then you take power 1 over p. Note that p doesn't have to be an integer or even a rational number. P could even be pi. So you can take a pi power of a positive real number and then take the pi root of it. So bear in mind that this is all defined using exponent logs. So power, you can have irrational powers of things. We normally look at powers of 1, 2, and the infinity norm. But there are all these other norms available as well. So then you can do the same thing on c to the n with exactly the same formulae and continuous complex valued functions on 0, 1 with exactly the same formulae again. For example, for the complex valued continuous functions, well, modulus is now the modulus of a complex number, but that's no problem. The modulus of a complex number will still give you, well, suppose the function f is a continuous complex valued function, then the modulus of f of x is still a non-negative continuous real valued function. So you can still take the p power, integrate it, and take the p root, and there's no problem. And it still gives you a norm. The fact that these are norms is relatively easy for 1, 2, and then the special case of infinity, and rather harder for the general value of p. And the general value of p is actually beyond the scope of this module to do this. You need to use things like Holder's inequality and Minkowski's inequality to check that things are working. So I'll leave that as an exercise to read if you want more details. So for more details on p not equal to 1, 2, or infinity, read about Holder's inequality. Probably Holder, actually. And also Minkowski's inequality. So you can find out about those, for example, in the book of Rudin, Real and Complex Analysis. But there are plenty of other places you can find them. As far as I'm concerned, you can quote that norm P is a norm as standard, and I won't be asking you to prove that unless I give it to you as a guided exercise. That's for P not equal to 1, 2, or infinity. For P equals 1, 2, or infinity, it's relatively easy to check that they are norms, and you could be asked to prove that. Okay, so your norm gives you a metric, and so you've got a metric space. And if you've got a norm space, we'll always give it that metric, and then that gives you a topology as well. But then you can ask, is that metric complete? And you may have wondered, unless you already know all about this, why is it that all the examples you look at in finite dimensional space, you seem to end up with a complete metric? And the answer, it turns out, that there's no choice. Any norm you try, if any norm you come up with at all on a finite dimensional norm space, finite dimensional vector space, is automatically complete. But that's not at all obvious, and we're going to prove it. So that's coming up. So that'll be one of the things we prove fairly soon. But in general, norms don't have to be complete, and some rather peculiar things happen. Every vector space can be given what's called a Hamel basis, just an ordinary vector space basis. There's another kind of basis called a Schauder basis, which we won't be dealing with in this module. But using Zorn's lemma, every vector space can be given a genuine maximal linearly independent subset, and it spans things using straightforward linear combinations, finite linear combinations of elements of that basis. That's the so-called Hamel basis for your vector space. With that, you can say, what is the dimension of your vector space? It could be finite dimensional or infinite dimensional. But if it is infinite dimensional, then there's still the possibility that it could be a countably infinite dimensional vector space or an uncountably infinite dimensional vector space. But it turns out a strange thing happens, that if you have a countably infinite dimensional vector space, you can never give it a complete norm. There are no complete norm on a countably infinite dimensional vector space. So there's a sudden jump. Finite dimensional norm spaces are always complete. Countably infinite dimensional norm spaces are always incomplete. And then you move up to uncountably infinite dimensional spaces, like some of the ones we mentioned already. And then the norms may be complete or incomplete, depending on which norm you choose. Now, we're mostly going to be interested in Banach spaces, but we want to see why is the theory so much better for Banach spaces, so we need to have a good supply of norm spaces as well, so that we can try out our results in the complete setting and in the incomplete setting. And it turns out that the theory is much better if you have completeness, and you get a lot of things for free that you don't get in the incomplete setting. So, we've mentioned R to the n and C to the n with the norms we've had so far. And as I said, it'll turn out that all finite dimensional norm spaces are complete. So it's not surprising that it turns out that those ones are complete. You can prove that they're complete directly if you want, but since that will follow from the general result, you can use that. We do want to know that if you put the Hilbert space norm, the 2 norm on, that it's complete. So it is actually important to know that. However, this is a standard fact about R to the n from metric and topological spaces. So we'll just be assuming that the result for the 2 norm, the usual Euclidean norm, and that's standard. The other ones, as I say, you can deduce from that, or deduce from the result coming up about all finite dimensional norm spaces. So it's entirely standard that what we'll call f to the n with norm 2 is complete. Would anybody like me to give you a quick proof of why that's true, or is everybody happy with that? So first of all, f to the n, of course, f is R or C. Norm 2 is the Euclidean norm. Would anyone like to see a very quick proof of the completeness of that, or are you happy that that's entirely standard? You'd like to see a proof? Hmm? Yes, okay, a proof. Okay. So what the proof I'll use, I'm going to base it on Boltzano-Weierstrass theorem. So this will be a very quick sketch. So y is f to the n with norm 2, the Euclidean norm, complete. We're going to use the Boltzano-Weierstrass theorem and facts about Cauchy sequence. Before I do this, as a metric space, if I'm using Euclidean norm, first of all, so note, as metric spaces, using the usual Euclidean norm, we know a lot about R to the n with norm 2, and we know about Boltzano-Weierstrass there. But you may wonder about C to the n if you haven't seen it before. So what's the connection, for a start, between C and, well, if you put the usual norm or modulus on C, what's it the same as in terms of the real numbers? C is isometric to R squared, yeah. We know that C is like R squared, and C to the n, more generally, with the Euclidean norm on C to the n, is isometric to R to the 2n. So we only really need to prove this result for R to the n. We'll get the C to the n's for free. So we just need to show that R to the n with norm 2 is complete for all natural numbers n. It's not topological invariant, but it is preserved by isometries, because convergence and Cauchiness get preserved by isometries. You don't really need the full force of isometry as long as you've got sort of Lipschitz continuity in both directions. But isometries are perfectly good. So if you've got two things that are isometric, or two metric spaces that are isometric, one is complete if and only if the other is. But homeomorphic isn't good enough. So that's worth noting. So if x and y are isometric metric spaces, then x is complete if and only if y is complete. we know that homeomorphic is not enough. But isometric is better. Isometric will take Cauchy sequence to Cauchy sequences and convergent sequences to convergent sequences as well. Homeomorphic will mean you can map the convergent sequences around, but it may not map Cauchy sequences to Cauchy sequences. And that's the problem with homeomorphisms. Isometries are better when you're dealing with metric spaces. Are you happy with that before I go on? Do you remember about homeomorphic metric spaces that are one complete and one not complete? Anyone remember an example of that?
R and 0, 1.
Yes, that's right. The real line is homeomorphic to the open interval 0, 1. With the usual metrics, the real line is complete, but the open interval 0, 1 isn't. They're homeomorphic, but they're not isometric. So that's why that can happen. That's an example we had from earlier in the notes. Okay, so we'll do R to the n with the 2 norm, and then you get R to the 2n will be some of those, which means you get the C to the n's as some of those as well. So here's your sketch proof of the completeness of R to the n with norm 2. So I'll underline my vectors for once. I can't use n though. N is in use. So let xk be a Cauchy sequence in R to the n with norm 2. Well, standard fact, Cauchy sequences are always bounded. Little exercise to check that. So if you never check that for yourself, you should check it. So then xk is bounded. By Boltzmann and Weierstrass theorem, which is valid in finite dimensional space, a bounded sequence must have a convergent subsequence. So this is a sequence with a convergent subsequence. Now, of course, a sequence which has a convergent subsequence doesn't usually have to converge. Who can tell me a sequence which doesn't converge, but which has got a convergent subsequence? Minus 1 to the n is a nice bounded sequence in R. Minus 1 to the n is bounded. It's got some convergent subsequences, but it doesn't converge itself. But it's not a Cauchy sequence. There's another standard fact that says if a Cauchy sequence has got a convergent subsequence, then it does have to converge to the limit of that subsequence. That's because you go along this subsequence, you get closer and closer along that subsequence to this point. But a Cauchy sequence is very nice because the terms are close to each other as well as you go along. So if you go far enough along, the terms are all very close together, and some of those terms are very close to this limit you're trying to get to. So another little exercise to prove this standard fact. Whenever a Cauchy sequence has a convergent subsequence, the Cauchy sequence must actually be convergent. Of course, it has to converge to the limit of that subsequence you found. And I've told you the reason. Go far enough along, the terms are very close to each other, and they're very close to, well, some of them are very close to that limit. But since they're all very close to each other by that point, they're all very close to that limit. A little bit of exercise there to get that to work. Okay? So you finish off by saying, since xk is a Cauchy sequence of a convergent subsequence, xk must converge. So every Cauchy sequence converges. Now that's a sketch which, to finish the details, you need to check those two exercises for yourself. You're allowed to quote those as standard facts. So you should check those exercises for yourself. And unless you're asked to prove those exercises, you're allowed to quote those facts as standard to help you prove other things. So, yes. Well, it works in, we know it works in R to the n with Euclidean norm. That's where we know it works. And any time it works, you get completeness. Since there are some incomplete norm spaces around, those are places where Boltzmann-Weierstrass doesn't work. So this Boltzmann-Weierstrass property is pretty much, I suppose it's pretty much equivalent to completeness, because if you've got it, you can use this proof. And well, okay, it's not quite true. Okay, so it's not equivalent to completeness. Completeness doesn't imply the Boltzmann-Weierstrass property. That's the way around that doesn't work. In finite dimensions, you're okay, as we're going to see that everything works. But if you're in infinite dimensions, in fact, the Boltzmann-Weierstrass theorem is never true. Not true for any infinite dimensional norm spaces at all. So that's a warning for you and for me. That's not obvious. That's not obvious, but it comes from Ries's geometric lemma. So this is very much a finite dimensional result. Since we're going to discover that all finite dimensional norm spaces are complete, we will, along the way, we'll essentially see that Boltzmann-Weierstrass works. Boltzmann-Weierstrass does work for all finite dimensional norm spaces too. Gosh, where were we? Okay, so that's the proof of the completeness of R to the m with the usual Euclidean norm, and C to the n as well. Any questions about that? Okay. You can do those two exercises for yourself. Okay, so if you use the uniform norm on CR of 0,1 or CC of 0,1, you're okay. It turns out they're complete. But if you use one of the other norms we've mentioned, they're not. So like if you do the integral of the modulus, or even if one that looks sensible, like integrating the squares of the functions, integrating the squares of the modulus, using the sort of what looks like a Hilbert space norm, but you end up being incomplete. You have to complete it afterwards, which will then take you to the usual Hilbert space of square integrable functions. But when you start with just continuous functions, it's not complete. Now, there's an awful lot of stuff to fill in the details of there, and I'm going to tell you about some of that. Before I go off and give you some of these details of some of these results, I want to note that, of course, there was nothing special about the closed interval 0, 1. We could have done any closed and bounded interval, but much more generally, we could have worked with any compact Hausdorff topological space. And you can still define the real-valued continuous functions on it and the complex-valued continuous functions. Non-empty would be a good idea, because otherwise there aren't very many interesting ones. And then you can define the uniform norm again. And this is because of the boundedness theorem. So again, this time you get if you've got f from x going to f equals r or c, as usual, continuous, then norm f infinity is, again, the supremum of mod f of x, where x is in your space, and again, the boundedness theorem says that supremum is actually achieved for continuous functions. So it's actually equal to the maximum again. There's a boundedness theorem valid for all compact Hausdorff spaces that a continuous function defined on a compact Hausdorff space, taking values in the real numbers, or indeed the complex numbers, will be bounded and attain its bound in this sense. Well, okay. Now, you start with a continuous f-valued function. By the time you take mod f of x, it's a continuous real-valued function. And again, you're bounded and achieve your bounds. In particular, you get a maximum modulus somewhere. So there's an awful lot of detail in there, all based on the following. Sorry, any questions about that slide before I move on and tell you a bit more about some of the detail? Okay, so what do you need to know to get started on this sort of thing? Well, there's some stuff about uniform limits and pointwise limits. Now, I'm going to assume you're familiar with pointwise convergence and uniform convergence, but you may want to revise some of that, and I've got some screencasts online about uniform convergence and pointwise convergence, so you should probably revise those if you're not very familiar with them. So, revise uniform convergence and pointwise convergence. And I've got screencasts available from my blog, for example. So, this norm infinity is the norm associated with uniform convergence. Oh, sorry, is there something? Yeah, it just went too high, is that right? Uniform convergence is a convergence associated with norm infinity. Norm infinity says two things are close together if they're close uniformly throughout the set or throughout the space. And what you really want is that you want to know certain facts about this. And now, in mathematical analysis, I didn't prove this result, but it's a general fact that a uniform limit of continuous functions is continuous. And I'm going to prove that for you. So suppose you've got a sequence of continuous functions, and they tend uniformly on your, even on your topological space if you want, to another function. Then you can prove that the limit is continuous as well. So it works quite generally, real or complex valued functions, and it works for non-empty, compact Hausdorff topological space instead of 0, 1. Let's see, which version shall I prove for you? I'll prove the version on 0, 1, but you can see how to make it work for more generality. So let Fn be a sequence of, and I'll do real valued functions, but again, you can modify this to work for complex valued functions. Continuous functions from 0, 1 going to R. And I'll have another function, and let f be any odd function from 0, 1 to R. No idea what it is yet. So it doesn't have to be, at the moment, a continuous function. Suppose that Fn tends to F uniformly, and I'll have maybe remind you what that means. Then F also must be continuous. Okay, how can we prove that? Well, first, we should remember what uniform convergence means. Can anybody remind me of a definition of uniform convergence for a sequence of functions? Yes? So you can look at the difference in values between fn of x and f of x, and then take the supremum over the interval and say that supremum must tend to 0. Yeah, that will work. Bear in mind that as far as you know before you start, you don't even know at first that f is bounded. So the supremum could be infinite for all you know. But you still, in fact, it follows that that can't really happen in this case. So you can sort of eliminate that. But I've just assumed f is any odd function at the moment. So you can do that with the supremum, in which case you can talk about the uniform norm. But the uniform norm is usually defined on bounded functions. And continuous functions are bounded on the closed interval. So then you could use the uniform norm. But we don't even know that the function f is bounded yet. So it's even scary to use the uniform norm at all. And so that supremum, you said, might be infinite for a while, but you would still insist that it tends to 0. And that's okay. And the sort of most general definition is Fn tends to F uniformly. Well, here's one meaning. Tells us the following. For all epsilon greater than 0, there exists a capital N natural number so that for all the later terms and for all points in the interval, and all x in naught 1. So this capital N is working in terms of epsilon. This capital N is working for all x at the same time. And for all of those, we have modulus of fn of x minus f of x. Most people say smaller than epsilon. Smaller or equal to epsilon will do. I'll say smaller than epsilon just to fit the standard, most standard version of it. So notice that n depends only on epsilon, doesn't depend on x. So from some point on, the functions are all very close to the limit function. Again, I say a lot more about this in the screencast in uniform convergence and pointwise convergence, and so you can have a look at that. I do things slightly differently there. I talk about function balls, curvy strips. What does it mean to say a function is close to another one uniformly? You can have some fun reading up on that in more detail. But here I'll just work directly from the definition, and now let's prove that the function f is continuous. And this is either called a 3 epsilon proof or an epsilon over 3 proof, depending on the version of it you do. I'm going to do an epsilon over 3 proof. The idea is that you end up, you want to get something less than epsilon, and it turns out you have to add up 3 quantities. So in order to make sure you still end up less than epsilon, you ensure that those quantities are each epsilon over 3, or at most. The alternative is to use epsilons everywhere, in which case you end up showing something else with less than 3 epsilon, which is as good as epsilon, really. So depends on your mood which version you go for. I'm going to do the epsilon over 3 version. So let x naught be in naught 1. We're going to show that f is continuous at x naught. So, you let epsilon greater than naught. What you've got to do is you have to show that the sum delta, so that if you're close enough to x naught within delta, the function values f takes will be within epsilon of the right value. We show that there exists a delta greater than naught such that we haven't done it yet. This is what we have to show. We show that there exists a delta greater than naught so that for all x in naught 1 with modulus of x minus x naught less than delta, we have modulus f of x minus f of x naught is smaller than epsilon. That's the definition of continuity in terms of epsilon delta. And that's what we've got to prove. So we'll start with an epsilon over 3. So since fn tends to f uniformly on naught 1, there exists a capital N in the natural numbers so that, and I'll just say that that particular one gets within epsilon over 3. So at some point you get within epsilon over 3. And I won't worry about the later ones. So that for all x in naught 1, we have modulus of fn of x minus f of x is less than epsilon over 3. Remember, you could do it for any given epsilon, you can find an n. So I'm choosing the capital N that works for epsilon over 3. You have to go a bit further to get to epsilon over 3, but you know you'll manage any positive quantity. So that's not bad. We've got a good approximation to our function. we got within epsilon over 3 using this function. And this function fn is continuous. So since capital N is continuous, from 0, 1 goes to R, it's continuous at x 0. So we can choose a delta greater than 0 so that for all x in 0, 1 within delta of x 0, we have for this particular fn modulus of fn of x minus fn of x 0 is more than epsilon over 3 again. Well, usually when you're doing continuity you have an epsilon. But again, if I make delta smaller, I can get this other positive quantity, epsilon over 3. So if you're close enough to x 0, this particular continuous function fn, which we know is a good approximation to f, stays very close. I claim that this delta works for f. This particular delta works for f and the original epsilon we started with at the point x 0. So we claim this delta now works for f, epsilon, and x 0 as above. So what do? You say, suppose x is close to x 0. Well, if you're within delta of x 0, then we know that mod f of x minus f of x 0 is small. That's smaller than epsilon over 3. But we also have two other estimates. Also, modulus of f of x minus fn of x. What can you tell me about that? How do we choose capital N? It's a bit further up your page. How do we choose capital N in the first place? We choose capital N to do something with epsilon over 3. So what we did was we chose it so that it was uniformly close, Fn was uniformly close to F within epsilon over 3 of it. So that's less than epsilon over 3. But it was uniformly close. And so, of course, you've got that for x. You also have it for x 0. Now we put it all together. Modulus of f of x minus f of x 0, we want to know how much can that be. Well, we use our successive approximations. We say f of x is about the same as fn of x is about the same as fn of x 0, and fn of x 0 is about the same as f of x 0. So that's equal to the modulus of f of x 0 minus fn of x 0, f of x minus fn of x So this is just going to be adding and subtracting the same things, plus fn of x minus fn of x 0 plus fn of x 0 minus f of x 0. I haven't done anything here except add and subtract some terms. But what I've done is I've expressed it in terms of the fact that I know that fn is a good approximation of f, and fn I know doesn't vary too much between fn of x and fn of x 0. And again, Fn is a good approximation to F. So I split this up into bits that I already know are small. By the triangle inequality, that's less than or equal to modulus of f of x minus fn of x, which we know is small, plus modulus of fn of x minus fn of x naught, which we know is small, plus the modulus of fn of x naught minus f of x naught, which we know is small. In fact, we know that each of them is less than epsilon over 3, so that's less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is equal to epsilon. And we've finished. Now, what I invite you to do is, when you look back at the, if you do look at the section on uniform convergence and pointwise convergence, think in terms of some of these curvy strips and what it means to be a really good uniform approximation to a function. And then have another look back at this proof and see what it's really saying. Okay, we better stop there for today.